Welcome to today the session, the physics related to the heat and thermodynamics. And first of all, this is the Nagabhushanam, the Department of Physics, K.B.N. College. In this session, we will learn about some topics related to the main topic is the thermodynamics. In this topic, the subtitles we will learn in this session. The first topic is the indicator diagram, and the next one is the Carnot's engine, and third one the entropy, and the last one the temperature entropy diagram. And before we going to these topics, we must need some basics like what is the temperature and what is the heat and what is the isothermal process and what is the adiabatic process and the reversible process and the irreversible process and what is the system and what is the surroundings. There is the basics are must required to understand clearly these topics. So first of all, what is the thermodynamics? So the thermodynamics, it is a branch of physics, and it explains the transformation of the heat energy or the thermal energy into the work, or the work convert into the heat energy. That means there is a transformation between the temperature and work and vice versa. And the system means some matter is bounded by the closed surface. The arrangement is called the system. And for example, some ideal gas is taken in a cylinder with frictionless and moving piston and non-conducting walls and perfectly conducting base. Generally, it is considered as the system. And surroundings means outside the system is called the surroundings, and generally we take in the surroundings the environment. And the next is the temperature. The temperature, the thermal property of the body, which gives the relatively the body's hotness or the coldness, and it is whether it explains the thermal equilibrium with the other body or not. And the heat energy means it is a form of energy, and this energy is transferred between the bodies by the temperature difference. So the heat energy is nothing but the energy which transferred from one body to another body, or from one system to the surroundings, or the surroundings to system, or between two systems due to the temperature difference. And there are two types of the process generally. One is the isothermal process and other one is the adiabatic process. In isothermal process, there is any system, there is the gas, and it has some qualities like a particular pressure and volume. And suppose the volume decreases, the pressure increases. So there is a change in the pressure and volume. Yet maintained the temperature is constant. The process is called the isothermal process. That means the process in which the pressure and volume changes, but the temperature remains constant, then it is called as the isothermal process. And in isothermal process, the Boyle's law is the holds good. That means the Boyle's law is obeyed in isothermal process, that is Pb is equal to constant. And in another process, that is the adiabatic process. In adiabatic process, there is no chance to exchange the heat energy between system and surroundings. But in isothermal process, there is chance to exchange the heat energy between system and the surroundings to maintain the temperature is constant. So Boyle's law is obeyed in isothermal, but in adiabatic the Boyle's law is not obeyed, but the Poisson's equation, that means P V power gamma is equal to constant is obeyed in adiabatic process, where P is the pressure and V is the volume and gamma is the ratio between two specific heats. So that means P V for gamma is equal to constant is holds good in adiabatic process. And there also in the system there is frictionless and a moving piston, and suppose the volume decreases, that means there is work done on the system. Suppose the gas expands, that means the volume increases. In this case there is work done by the gas. So generally we taken there is a polarity by gas, it is treated as the positive, and work done on the gas and the system, it is taken as the negative. So in isothermal process the work done, the formula is RT log Vf by Vi, the base E, where R is the universal gas constant and T is the temperature, and Vf and Vi are final and initial volumes respectively. In adiabatic process, the work done by the gas or on the gas is expressed by the formula R by gamma minus 1 into T1 minus T2, where T1 is the initial temperature and T2 is the final temperature. So these are some basics in thermodynamics, and by these basics we can easily understand the topics like the indicator diagram and Carnot's engine like. So first of all, what is the indicator diagram? So diagram, it is the graph drawn between the pressure and the volume. So here the volume values of a system or the gas is taken along the x-axis and the corresponding pressure values along the y-axis. So the indicator diagram is nothing but the graph between P and V. So the indicator diagram is also known as the PV diagram also. So indicator diagram or the PV diagram is it is the graph between pressure versus the volume. Here the pressure values along the y-axis and the corresponding volume values along the x-axis. So here in the diagram there is a curve AB. So here the A is the initial state and B is the final state. So here at A the volume is V1 and at B the volume is V2. So from the graph we observe that V2 is greater than V1. So here from A to B means there is the gas expands, that means work done by the gas. So the indicator diagram it represents the change the system. That means it gives the initial state and the final state or the intermediate state also. That means in between A and B. So one of the best application of this indicator diagram is the area under the curve. That means the area bounded between the curve and the x-axis gives the amount of work done. So by using this indicator diagram we can calculate the efficiency of Carnot's engine also. So the indicator diagram represents the initial state or the final state or the intermediate state of a system also. So it is the indicator diagram. So indicator diagram is it is the graph between pressure and volume, pressure values along the y-axis and the corresponding volume values along the x-axis. So it is the graph between P versus V. And the main topic in this session is the Carnot's engine. So here first of all the engine, its main function, it is the useful or it is the device useful to convert the heat energy into the mechanical work. So it is the ideal engine, but practically it is not possible. So here the Carnot's engine, its main parts are represented here. The first part is the working substance, and the source and the insulating stand and the sink. So here the working substance means some gas is enclosed in a cylinder, and the cylinder consisting the piston, and it is frictionless and non-conducting, and the walls also the non-conducting, but its base is the perfectly conducting. So the working substance means some ideal gas enclosed in a cylinder, and the cylinder made by non-conducting and frictionless piston and non-conducting walls and perfectly conducting base. And the next part of this Carnot's engine is the source. It is a hot body. It maintained the temperature T1, and its peculiar character is its temperature remains constant by even though there is a large amount of heat drawn from this source. So source, the character is its temperature T1 is the remains constant. It is a hot body, so it has a high thermal capacity. And the sink, its temperature generally represented the letter T2. It is the cold body, and its temperature also remains constant even any amount of heat added to this part. In case of the source, T1 is the constant by the heat drawn from the source, but here the sink, even the large amount of heat added to it, its temperature is not increased. Its temperature is also remains constant at T2. And the last part of this Carnot's engine is the insulating stand. Here the working substance base is the perfectly conducting. So to make the entire system is perfectly isolated, non-conducting, it must place some non-conducting stand. That is the non-conducting stand is also known as the insulating stand. So suppose the working substance is placed on the insulating stand, there is no chance to exchange the heat energy between system and the surroundings. So these are the main four parts of the Carnot's engine. So the main function of the Carnot's engine is it is a device. It is useful to convert the heat energy into the mechanical work, and the parts are working substance, source, sink, and the insulating stand. Here the source is the hot body and sink is the cold body, and working substance is the ideal gas is enclosed in a cylinder, and the entire the working substance or the system is made by isolated by placing it simply on insulating stand. These are the main four parts of the Carnot's engine. And it is the Carnot cycle. So here the working of the Carnot's engine is explained on the basis of this Carnot's cycle. So Carnot cycle means it is the just PV or the indicator diagram, and there are the four operations are here. One is the AB, and the second one is the BC, and third one is the CD, and the last one is the DE. The starting is the A and ending also A, so it is the cycle. So here the initial state of the working substance is denoted in PV diagram or Carnot cycle is A P1 V1. So initial pressure P1 and volume V1, and the isothermal expansion in final state is B denoted, and here the quantities of the system, pressure is the P2 and volume is the V2. So here the isothermal is expansion is here represented by the curve AB, and in this case the working substance first of all the placed on the source, and here Isothermal expansion means here the piston is moving upwards. That means expansion. That means work done by the gas. So here some heat energy decreases to do the work by using its internal energy. So there is chance to decrease its energy. So there is chance to decrease the temperature. But it is the isothermal process here. The temperature remains constant. So for this purpose, the working substance is drawn the heat energy from the source, and the source temperature is the T1, and suppose Q1 is the amount of heat energy taken from the source by the working substance. So along the AB, it is the isothermal expansion. First of all, the working substance is placed on the source. Gas expands, and that means work done by the gas, and the working substance absorbs the heat energy Q1 at constant temperature at T1. So this isothermal expansion, the process is represented by the curve A, P1 V1 to B, P2 V2. It is the first operation in the Carnot's engine. And in the second step, it is the adiabatic expansion. So adiabatic expansion is represented by the curve BC, and in adiabatic expansion, in adiabatic process, there is no chance to exchange the heat energy between system and the surroundings. So here the working substance is must placed on the insulating stand, and the gas expands. So there is no chance to take the heat energy because the base also the non-conducting. So its temperature decreases, and the temperature is the first of all at B is the T1, and there is a decrease in temperature T2. That means the temperature falls from T1 to T2, and in adiabatic expansion there is for temperature falls, and this adiabatic expansion is represented by in PV diagram by the curve the BC, and at C the pressure is P3 and V3, and in third step there is the isothermal compression. See here the working substance is placed on the sink. So here it is the compression, that is work done on the gas, but it is the isothermal process, and there is to chance to increase the internal energy and hence the temperature, but it is the isothermal process, the temperature maintained as the constant. So here the heat energy is rejected to the sink, and sink temperature is the T2. So here the heat energy given to sink by the substance is the Q2, suppose at a constant temperature T2. Q1 is the absorbed heat energy from the source at a temperature T1, and Q2 is the rejected heat energy to the sink at constant temperature T2. And suppose at D the parameters of the pressure and volume of the gas are P4 and V4, and the final step is the adiabatic compression, and it is the adiabatic process, and in adiabatic process the working substance is placed on the insulating stand, and it is the compression, so work done on the gas. So there is no chance to exchange the heat energy, so the temperature again increases from T2 to and the initial temperature T1. So here there are the four operations. They are isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression, and they are represented by curves AB, BC, CD and DA respectively. In isothermal expansion, the main point is the working substance is placed on the source, absorbed heat energy Q1 at constant temperature T1, and in adiabatic expansion the working substance is placed on insulating stand, the temperature decreases from T1 to T2, and in third phase the isothermal compression, the working substance is placed on the sink. The rejected heat energy is Q2 at constant temperature T2. In adiabatic compression, the working substance is placed on the insulating stand. Here the temperature rises from T2 to T1. It is the one complete cycle. This is called the Carnot's cycle. These are the 4 operations. So here along AB work done by the gas, along BC work done by the gas, along CD work done on the gas, and DA work done on the gas. So these are the 4 operations: isothermal expansion along AB, adiabatic expansion along BC, and isothermal compression along CD, and the last one, the adiabatic compression along DA. So here along AB isothermal expansion, the work done by the gas is W1 suppose, and its formula is given by RT1 log V2 by V1 base E. See here the W1 is nothing but the absorbed heat energy from the source Q1, where R is the universal gas constant and T1 is the temperature of the source, and V2 is the final volume, and V1 is the initial volume. It is the work done by the gas along isothermal expansion from A to B. And here this work done is also equal to the area bounded between the curve AB and x-axis. So the A, B, B dash and A dash, AB, B dash, A dash and A. And it is the adiabatic expansion. Here the work done is equal to R by gamma minus 1 into T1 minus T2, where R is the universal gas constant, and gamma is the ratio between 2 specific heats, and T1 is the initial temperature, that means source temperature, and T2 is the final temperature, that means it is the sink temperature. And here the area the work done is also in terms of area, it is B, C, C dash, B dash and B. And in third operation it is the isothermal compression along CD, and here the work done is W3. Here work is done on the gas. So here the rejected heat energy Q2 is also equal to W2, and it is the isothermal process. The formula RT2 log V4 by V3, where T2 is the temperature of the sink, and in terms of the area it is equal to C, C dash, D dash, D and C. And here V4 by V3 is also expressed V3 by V4 by put the minus symbol. Here the minus sign indicates there is work done on the gas. And the final step, it is the adiabatic compression along DA, and it is the adiabatic process. So the work done on the gas is R into T1 minus T2 by gamma minus 1, and in terms of area it is D, D dash, A dash, A, D. So these are the 4 work done. Out of 4, 2 are work done by the gas, and the last 2 work done on the gas. So the net work done means it is the sum of these 4 works. So here the efficiency of the Carnot's engine is, it is defined, it is the ratio of the net amount of work done by the engine to the heat drawn from the source. Here, the work done by the engine means it is the sum of four works W1, W2, W3, W4. That means W1 plus W2 plus W3 plus W4, and heat taken from the source means it is denoted by generally Q1, and Q1 is nothing but W1. So by substituting these values and simplification, finally we get the expression: the efficiency of Carnot's engine is Q1 minus Q2 by Q1. It is the efficiency of Carnot's engine in terms of heat energy, where eta is the efficiency of Carnot's engine and Q1 is the amount of heat taken or drawn from the source, and Q2 is the amount of heat energy rejected to the sink. So here efficiency of engine means it is the ratio of the net amount of work done by the engine to the heat taken from the source. The next point is the entropy. Generally entropy is denoted by the letter S, and it is defined as it is the ratio of the heat energy to the temperature, and here the heat energy is Q and the temperature is the T. So S is equal to Q by T. Generally S is it is the absolute value of the entropy of a system, and it is calculated some difficult. So but we can easily calculate the change in entropy, and its unit the Q is the energy, so joule, and the temperature it is the Kelvin. So the entropy measured in terms of joule per Kelvin, and there is the change in entropy ds is equal to dq by t, where dq is the there is a change in heat energy, and ds is the change in entropy at a temperature at T. Suppose there is absorbed heat energy by the system, there is a increase in entropy. Suppose the system is rejected some heat energy, then there is a decrease in entropy. So entropy increases when the system absorbing the heat energy, and its entropy decreases by it loses some heat energy. And there are also two processes, one is the reversible process and other one is the irreversible process. The reversible process means the process in which all changes are occurring in direct process are exactly repeated in opposite order. That means work done by the piston in direct process, that means in reverse work done on the piston. That means work done by the system or work done on the system. Heat absorbed in direct process, heat rejected in opposite, and ice converts into liquid, and in reverse liquid again converts into ice like this. It is the reversible process. So in the reversible process the entropy remains constant. That means the change in entropy is zero. In irreversible process, the process it is not exactly reversible, it is called irreversible process. In irreversible process the entropy always increases, and the entropy and disorder means the how to change the entropy with respect to disorder, or disorder of how to change of a system with respect to the entropy. We know that in solids the atoms are very closely packed and they are arranged in systematic pattern. That means they are regular arrangement. So the disorder is very low in case of the solids comparatively liquids and gases, and more the molecules are the moving zigzag and randomly and most freely in gases comparatively and other states, solids and liquids. So the entropy is increased in liquid state comparatively solid state. So the disorder also increase. With respect to liquid to gas state, the entropy increases along with the disorder. So the entropy is also measured the degree of disorderness also. So as entropy increases, the disorder also increases. And the entropy of universe. In general, in universe, all processes are the irreversible process, and already we know that in irreversible process the entropy increases, so the entropy is always increase in universe. And here briefly what the entropy means. We know that the temperature is the remains constant in isothermal process. In the same way, in the adiabatic process also some physical quantity is maintained as constant, and that physical quantity is known as the entropy. So that means entropy is a physical quantity. It is constant in adiabatic process, just like the temperature in isothermal process. And here in reversible process the entropy remains constant, and in irreversible process the entropy increases, and the entropy increases, the desert also increases, and the entropy in universe is always increases. And the another topic is the TS diagram, like PV diagram. A PV diagram means it is the graph between P and V, P for pressure and V for volume. It is the TS diagram. So here T means it is the temperature, and S means it is the entropy. So just it is the graph drawn between temperature and entropy. And here the temperature value is along the y-axis, and the corresponding entropy temperature value is along the y-axis, and the corresponding entropy values along the x-axis. So here with the help of this TS diagram we can also calculate the efficiency of the Carnot's engine also. Here the TS diagram for Carnot's engine is a rectangular shape, AB, BC, CD and DA, and these are the four operations: isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. And in isothermal expansion along AP, the working substance on the source and work done by the system. And here the temperature is the isothermal process temperature constant at T1, but the absorbed heat energy is the Q1, so entropy increases from S1 to S2, but temperature maintained as constant, so it is a horizontal line AB. But BC is the adiabatic expansion, the working substance placed on the insulating stand, so there is no chance to exchange, so entropy remains constant at S2. It is the expansion, so work done by the system, so the temperature decreases from T1 to T2, so we get the vertical line BC. And CD is the isothermal compression, that means work done on the system. So here the working substance is placed on the sink at a temperature T2. So here the heat energy rejected is the Q2 to the sink. So the entropy decreases from S2 to S1, but the temperature is the constant at T2. So again we get the horizontal line CD. And the final operation is the adiabatic compression. It is denoted in TS diagram by DA line. And here the working substance is based on the insulating stand and work done on the system. There is no chance to exchange the heat energy. So entropy is constant at S1, but the temperature increases from T2 to T1. So again finally we get the vertical at DA. So the AB horizontal and CD horizontal, BC vertical and DA vertical. So finally on TS diagram, the Carnot's engine, the TS diagram shape is a rectangular shape. And with the help of the TS diagram we can also calculate the efficiency, that is eta is equal to it is equal to absorbed heat energy Q1, absorbed heat energy Q1 and the rejected energy Q2, and the available energy is the useful energy is Q1 minus Q2. It is converts into work, and according to the definition of the Carnot's engine efficiency, it is the amount of heat taken is the Q1 and the work done is the W. So according to the definition, it is the ratio of amount of work done by the engine to the heat taken from the source. So W by Q1, here W means Q1 minus Q2 and heat taken is the Q1, and it is finally we get efficiency is equal to 1 minus Q2 by Q1. And there are some useful that means advantages of the TS diagram. They are used in meteorology department, and they are also used to find the defects in the performance of the engine, and it is also useful to check the efficiency of the heat engine also, and it gives the work value of the value of the fuel used. These are some of the uses of the TS diagram.